Good morning friends, welcome back to Parnika tutorials. In this video, I want to discuss what is the need for virtual memory, what are the advantages of virtual memory, what is a page hit, what is a page fault, what is a page fault service time, how to compute the effective memory access time. All these concepts I will discuss in detail for you. So I request everyone to watch the complete video for better understanding. First, let me discuss what is the need for a virtual memory with an example. Let's consider that you have 1 GB main memory. Meaning is that your RAM size is 1 GB. You want to play a game of 4 GB and you have loaded this 4 GB game in your secondary memory. Meaning is that you have copied the game in your hard disk. Is it clear? Now, if CPU want to execute any instruction, that instruction need to be loaded into the main memory. Now, if you want to run a 4 GB game, according to the CPU, all that information will be loaded into the main memory. Now, if you have a 1 GB RAM, how can you load a 4 GB game, which is not practically possible? So, their virtual memory is required. Virtual memory give an illusion that even if your process size is greater than the main memory size, still we can run with the help of on-demand paging. What is that on-demand paging? I will discuss for you. Now you will have a question. Sir, if you have a 4 GB game, you are running with the help of virtual memory. But what is the restriction or the virtual memory? What is the maximum storage of the virtual memory? Means what is the maximum process size we can run? It depends on the secondary memory. So the virtual memory size will be depend on your secondary memory. Is it clear? Suppose let's take that your hard disk is 1 terabyte. So you can run a process of 1 terabyte. Is it clear? So that is what the restriction on the virtual memory. So it depends on your hard disk or the secondary memory. Is it clear? Now let me give an overview for you. Your secondary memory consists of several processes. Let's take the process 1, process 2, process 3 is there. Okay. Now each process is logically divided into pages and your main memory, some part of the main memory has been occupied by the operating system, and then you will logically divide the main memory into frames. And remember one important point, the page size will be equal to frame size. Is it clear? Now you will discuss about how the CPU will generate the logical address and then how it will be converted into physical address. Usually the CPU will generate the logical address only. Now the logical address consists of page number and then page offset. The memory management unit will convert the logical address to the physical address. The physical address will consist of frame number and then frame offset. Now let me discuss with a simple example. Let's take that your page size is 4 KB. Your page size is 4 KB. And then number of pages you have 1024 pages. Then if it is byte addressable, if your memory is byte addressable, if your page size is 4 KB, then you need 12 bits to store the page offset. So page offset will occupy 12 pages. So the number of bits required for the page offset will depend on the page size, as it is 4 KB. K is nothing but 2 power 10. And then 4 is 2 power 2. So you need 2 power 12, which is nothing but 12 bits are required. And then you have 1024 pages. If you have 1024 pages, you need 10 bits for representing the page number. So the number of bits required for the page number will depend on number of pages. So this is nothing but your logical address is 22 bits. So your logical address space is your 2 power 22 bits, which is nothing but 4 MB. Is it clear? Are you able to understand? 2 power 2 into 2 power 20, which is nothing but 4 MB. Now you know that page size will be equal to frame size. If your page size is 4 KB, then page size is also 4 KB. So frame offset also will occupy 12 bits. Let's take that you have 16 frames in your main memory. Then the number of bits required for the frame number is 4. So your physical address is 16 bits. So if you have 16 bits is nothing but 2 power 16. So your physical address space or your main memory is 2 power 16, which is nothing but 64 KB. So your main memory size is 64 KB and your process size is 4 MB. Still we are able to run with the help of virtual memory concept. Is it clear? Now you can ask me one thing. Sir, how the memory management unit will convert the logical address to the physical address? Let me discuss with a simple example. Let's consider that you have a process P1 has 7 pages. Out of these 7 pages, few pages are loaded into the main memory. Is it clear? Let's consider that you have process page number 0 and then page number 2 is currently available of the process P1. Is it clear? Are you able to understand? Similarly, process P2 page number 3 and page number 4 is loaded. Is it clear? This is the process P2 information. And process P3 page number 0, page number 1, page number 2, page number 3 has been loaded in the main memory. So this is the process P3. Is it clear? Now what is the advantage of this one? The advantage is that you are introducing the degree of multi-programming. You are improving the degree of multi-program. Meaning is that at a time you have 3 processes currently residing in the main memory. So the degree of multi-programming is improved with the help of virtual memory. So there are 2 advantages using the virtual memory. One is that even your process size is greater than the main memory size, we can run it, and even at a time we can have n number of processes can be residing in the main memory. So the degree of multi-program will become n there. Is it clear? Are you able to understand? So now if you look at process P1, what are the pages are there? Page number 0. Let's keep here. Process P1, page number 0, page number 2 is available. So page number 0 is available in the frame number 0. Page number 2 is available in the frame number 2. Is it clear? Now remember one thing. Each process will maintain its page table. The page table will consist of several information. One is that frame number and another one is that present or absent. The present or absent bit signifies that whether the particular page is available in the main memory or not. If present or absent bit is kept as 1, meaning is that the particular page is available in the main memory. If it kept as 0, then particular page number 1 is not available in the main memory. If it is not available in the main memory, in which frame it will be there? It will not be there. That information will not be there. So this will be 1 and remaining will be 0. Is it clear? Now you can ask me, the number of entries in a page table will depend on what? The number of entries in a page table will depend on number of pages of a particular process. So each page table size will depend different. Meaning is that because the page table size will depend on number of pages and page table entry size. Are you able to understand? The page table entry size will depend on number of bits are required for the frame number, present or absent bit. You will have a dirty bit. You will have what? Cache enabled disabled bit will be there, reference bit will be there, protection bit will be there. All these bits will call it as optional and compulsory bit is frame number. Is it clear? Are you able to understand it or not? Now you can ask me one thing. Sir, you are saying okay, each process will maintain its page table. Now where the page table will be stored? Whether that information the CPU knows it or not. This is very important question. Now remember one thing. If your page table size, let's take that your page size or the frame size is 4 KB. Now your page table size you got it as 6 KB. Now if your frame size is less than the page table size, can you load that page table in one of the frame? No. Remember one thing. Always the page table should be loaded into the main memory. Now if your page table size is less than the frame size, then we will load that particular page table in one of the frame of the main memory. Is it clear? Now your frame size is less than the page table size, then we will go for the multi-level paging. Is it clear? I hope you know what is a multi-level paging. Is it clear? I have discussed about the multi-level paging because the inner page table size is greater than the frame size, then the inner page table again will be divided into pages. That information will be loaded in the outer page table. So if you have the multi-level paging, the number of access will increase. Is it clear? Are you able to understand? Now, how the CPU will come to know? Let's take that in the frame number 6, page table of process P1 has been loaded. Is it clear? In the frame number 6, page table of process P1 has been loaded. Then how the CPU will come to know? CPU will have one register. In that register, it will store the page table base address. Okay, so let's consider that this address is 3000, the starting address. Base address is nothing but what? Starting address. Frame number 6, the starting address is 3000. So the page table of process P1 has been loaded in 3000. Is it clear? So that information will be there. Now let's take that CPU want to access the page number 2. The information which is available in the page number 2 of process P1. Are you able to understand? Then for this one, the page number 2 will be added. So it will go to the particular page. See, 3000 is the starting one. Are you able to understand? In 3000 address, the page table is there. So to that one, the 2 will be added. So it will go to this address. Are you able to understand? Then it will go to the frame number 2 because the page number 2 is available in the frame number 2 because there is a present or absent bit has kept as 1. Are you able to understand? Is it clear? Now, that's why if you have n number of processes are currently running, all the n number of processes need to be loaded, page tables need to be loaded in the main memory. Even the page tables will occupy some space of the main memory. That's why the researchers have introduced the inverted page table, but there are some limitations with the inverted page table. So that's why it become not successful. Is it clear? Are you able to understand it or not? So I have discussed what is the purpose of page table and where it will be loaded and how the CPU will come to know the starting address of the page table. Now let me discuss about the page hit and page fault, and then I will discuss about the page fault service time. Now let's take that CPU want to access the page number 0 of process P1. Now page number 0, you will go to the page tables entries. Okay, page number 0, present or absent bit is kept as 1. The meaning is that page number 0 is available in the main memory. If it is available, in which frame it is available? It is available in the frame number 0. So CPU has generated the logical address consists of page number as 2. Then memory management unit will convert into physical address consists of frame number as 0. So it will go to the frame number 0 and access the page number 0 information. So if CPU is trying to access a particular page, if the particular page is available in the main memory, that concept will call it as page hit. Now let me discuss what is a page fault. Let's take that CPU is trying to access the page number 3 of process P1. Now page number 3. Present or absent bit is kept as 0, meaning is that page number 3 is not available in the main memory. If it is not available in the main memory, then we will call it as page fault. Is it clear? Now if a page fault occurs, what will happen? We will discuss this one. This is very important concept to solve the gate questions and numerical questions. Please understand the concept carefully. Whenever a page fault occurs, there will be a trap signal will be generated, which is nothing but your interrupt. CPU is currently executing the process P1. Whenever a page fault occurs, the operating system will take control. So there is a context switching. Process P1 was currently running. Now operating system has taken the control. So there is a context switching. And the page number 3 of a process P1 is there in the secondary memory. So the particular page will be loaded into the main memory from the secondary memory. This process we will call it as swap in. Transferring the page from the secondary memory to the main memory is called as swapping. Once the swapping is done, the page number 3 has loaded in one of the frame. Then operating system will give back the control to the process P1. Again, this is what is called context switching. So the total time we will call it as page fault service time. Is it clear? Are you able to understand it or not? So whenever there is a page fault happens, there will be a two context switchings and the swapping. Now you will ask one more important question. I think maybe it is coming in your memory. Okay. Now you will ask that, sir, let's take that you have 6 frames in the main memory. Now all the 6 frames are full with some process page tables and the pages. Is it clear? Then if you want to do the swapping process, meaning is that you want to load the page number 3 of the process P1 in one of the frame. How you will do it? Then we will have the page replacement strategies. We have several page replacement strategies such as first in first out, optimal page replacement strategy, and we have LRU. In those replacement strategies, depend on the strategy, we will find the victim page, which page need to be removed from the main memory and then load it into the secondary memory, and then which page need to be loaded. Now you can ask me, sir, you want to remove the page number 0. Why you have to load it back into the secondary memory? Just you bring the page number 3 and load here. That's all. Why we need to store the page number 0 in the secondary memory? I will also tell this point. Please clear. Let's consider that page number 0 has been modified. Some information which is available in the page number 0 has been modified. So that's why we have in page table, there will be a dirty bit. A particular page has been modified, then dirty bit will be kept as 1. Meaning is that the page number 0 which is available in frame number 1 has been modified. If it is modified in the main memory, the information which is available in the main memory will be different to the information will be available in the secondary memory. Suppose let's take that you have written a C program, there a value is 2, here it is a value is 2, here is also a value is 2 initially. Now user has written some a plus plus or plus plus a and it has modified to 3, or user has modified it to 3. Okay, now it has been modified in the main memory, but it has not modified in the secondary memory. Then dirty bit will be kept as 1. Then whenever page replacement algorithm has to remove this page, then this page will be loaded back. The modified information will be loaded back into the secondary memory. Okay, so this process we will call it as swap out. Whenever a particular page has to be loaded from the main memory to the secondary memory, this concept we will call it as swap out. So page number 0 will be loaded into the secondary memory, then page number 3 will be loaded in frame number 0 of the main memory. So this one we will call it as page replacement algorithms. Is it clear? I hope you have understood. Now you can ask me one important thing. Sir, how can we compute the effective memory access time? Yes, your question is valid. If there is a page false, if there is a page hits, what will be effective memory access time? Meaning is that whatever the page number the CPU want to access, how much time it will take. This concept we will call it as effective memory access time. To know that one, let me use some terminologies. Page fault ratio is 60% and then page hit ratio will be 40%. What is meant by this 40% of page hit and 60% of page fault? Meaning is that let's take that CPU is trying to access 100 pages. Out of the 100 pages, 60 pages are not available in the main memory. If they are not available in the main memory, we will call it as a page fault. So page fault rate is 60%. Then out of 100 pages, 40 pages are available in the main memory. If it is available in the main memory, we will call it as page hit. So page hit rate is 40%, page fault is 60%. Let me keep the page fault as P percentage. Is it clear? So then effective memory access time will be P. If it is a page fault, we have to do the page fault service time. Okay, meaning is that loading the page from the secondary memory to the main memory. Then we need to access the particular page from the main memory also. This will be the time taken if there is a page fault. If there is not a page fault, meaning is that 1 minus P will be the page hit. If this is a page hit, then main memory access time only will be taken, because if the particular page number 3 of process P3 the CPU is requesting, it is available in the main memory, then directly you will access from the main memory. Is it clear? So that is about this formula. So how can we compute is, let's keep the page fault rate as P, and this is the page fault service time as I am keeping it as PF, and then you are accessing the main memory time is M. Is it clear? Then 1 minus P into main memory access time is M. Let me expand this one. P into PF plus P into M plus M minus P into M. Am I right? So this plus P into M and this minus P into M can be cancelled. So this expression can be written as P into PF plus M. Is it clear? Where P is the page fault rate and PF is the page fault service time and M is the memory access time. Is it clear? Are you able to understand? Now we will discuss one important concept called trashing. If the number of page faults are very high, the meaning is that whatever the CPU is trying to access, that particular page is not available in the main memory. Then all those pages, suppose let's take that 99% there is a page fault. So CPU is trying to search for the 100 pages, 99 pages are not available in the main memory. They are available in the secondary memory. So all these 99 pages need to be loaded in the secondary memory. So the page fault service time will become more. So if the page faults are very high, your effective memory access time will be completely depend on your page fault service time only. Is it clear? Are you able to understand it or not? Because your page fault is high, so then page fault service time will be increasing. This part will be increasing and this part will be negligible. So this concept will call it as trashing. If your number of page faults are very high, you can ask me why the page fault will happen. Let's take that process 6 pages are there. Now we are saying on-demand paging. Whenever the CPU requests for a particular page, then only we will load it. So whenever CPU is accessing the particular page first time, that page will not be available in the main memory. So there is a page fault. Is it clear? Then we will go for the page fault service time. Is it clear? So with this explanation, I hope you have understood what is the need for a virtual memory, what are the advantages of virtual memory, what is a page hit, what is the significance of page table, where the page table will be stored, and what is a page fault service time, and how can you compute the effective memory access time. If you still have any doubts related to the concepts whatever I have discussed in this video, feel free to ask me in the comment section. I will try to answer your queries as early as possible. Thank you for watching the complete video. Have a nice day.